Good evening, Partha sir.
Good evening,
Hello.
Partha sir.
Good evening. Good evening.
Yeah.
Ma'am, recording is on and we are live on YouTube.
Oh, sorry. Okay.
Uh-huh.
So, on behalf of Nasi Daily Chapter, who has organized this 10-week course started on 27 July on physics learning with problem and conceptual based approach. So I welcome all the participants and the first speaker of the day, Dr. Partha Goswami, to the webinar. So he is going to give a talk on quantum mechanics. So can I request you to share the next slide?
My slide is stuck, I think.
Mansi,
One second.
you click on your this slide and then shift. First click on this slide and then click, then shift.
Yeah.
Next one, please.
Yes.
So let me introduce the speaker to the participants. So Dr. Partha Goswami, MSc, MPhil and PhD from University of Delhi, is presently an Associate Professor in Physics in Deshbandhu College, University of Delhi. He has done his graduation with first position from St. Xavier's College, Ranchi. He has been teaching mathematical physics to BSc Physics honors students for the past 30 years. His area of specialization is condensed matter physics. He has 32 research papers to his credit, mostly under sole authorship, published in prestigious journals of physics. So, welcome you, sir. And I request you to start your talk and kindly share his PPT.
Yeah, this PPT sharing will be done by.
Yes, I am going to share.
I'm asking her only. I'm asking her only, sir.
Okay, so I would now make a beginning. Please focus on the first slide.
Sir,
and also video as well.
Sir, which presentation you want me to show? It's the last presentation, the one you were taking
number 2,
last class.
Number 2, problems in quantum physics. Number 2.
Okay. Okay.
Yeah. So, ma'am, can I make a beginning now? Hello?
Yes, sir. Please start. You can start. Sir, you can start.
Sir, your slide is visible. You can start. Yes, sir.
I have stopped the video because it interferes with
Sir,
audio.
no issue. Sir, absolutely no issue. There is no problem, sir.
Right. So, in the first slide, students can see that we want to talk about the expectation value of an operator. I think I've already given the notion of operator. All observables in quantum mechanics are represented by operator. Operator could be differential operator, or they have equally well representation in terms of matrices. Now, we are, of course, following, in fact, Schrodinger approach as well as the matrix mechanics approach. Schrodinger approach was, of course, initiated by Erwin Schrodinger himself, and the matrix approach was initiated by uh, Pauli, Werner Heisenberg, and not many people. Of course, there is a third approach as well to quantum mechanics, which is Feynman's path integral approach. But here, I would mix a bit of Schrodinger, a bit of the matrix approach. And in the first slide, I am totally dependent on the Schrodinger approach, that is approach involving differential equations, differential operator, and so on. So we have we have an operator which has some derivative representation, and suppose I have wave function of a particle, a system of particles to be psi x, and I wish to define expectation value of the operator on the wave function psi x. How do I define it? I have clearly shown that the operator A is to act on psi, and on the left side, psi being a complex scalar, on the left side, we multiply the complex conjugate of psi, and we are generally dealing with one-dimensional system. So we are integrating over all values of x. This is the basic definition of expectation value of an operator A. Now, operator acting on a state, say psi, will give me an eigenvalue, call it as small a, and I will get back the state psi as well. So action of an operator on a state of a quantum system is physically interpreted as, because small a will be a number, so physically it could be interpreted as stretching, shrinking of this state. If small a is greater than 1, we have stretching, small a less than 1, then we have shrinking. Or if small a is equal 1, then I have state remaining as it is. So operator is an identity operator. So operator A acting on psi will give me its eigenvalue psi, and state psi I will get back. So eigenvalue will now get sandwiched between psi star and psi. Eigenvalue, as I said, is a number, nothing to do with any operation. So number can come outside the integral. We shall have therefore psi star psi dx, which is integrated over all space. So that will give me total probability, which is 1. And therefore, the expectation value of the operator is turning out to be the eigenvalue of this operator. One may relate with the term eigenvalue, eigenvector, etc. more with matrix. So I would like to add at this point that the operator, any operator for that matter, can have differential derivative representation, as well as the representation could be in terms of matrices. So say 2 cross 2 matrix, 3 cross 3 matrix, like that, n cross n matrix. So there would be a matrix representation of operator. And once we have that, the word eigenvalue and corresponding eigenvector, etc., become more palatable. So with this, we go to the second slide. Second slide, please. So please, second slide.
Dr. Mansi, please shift this slide.
Yeah, I'm
Second
doing.
slide.
Actually, my cursor is little stuck. Yeah, that's all right.
Yeah, second slide. Suppose I have an operator. I have already defined its expectation value. And now operator, I want how this operator evolves in time. That means I want the equation of motion of the expectation value of this operator. So one can see that this is equal del t of psi star a psi dx, which is easy to follow. That is how expectation value has been defined. So we have now derivative of product of three quantities, three entities, psi star a and psi. We have applied product rule in the second step and integrated over all x. The quantity, the middle one, the term middle one, psi star dA, del A, del T, psi integrated over dx, integrated over x is the expectation value of del A, del T, del A, del T. So we have put it outside, and remaining two terms, the one in the left and one in the extreme right. On the remaining two terms, we have applied the time-dependent Schrodinger equation, which gave me I by h cross integral over h is Hamiltonian, of course, h psi within parenthesis star a psi minus psi star ah psi dx. One can easily see, applying time-dependent Schrodinger equation, that gets this. Now, Hamiltonian is Hermitian. Hermiticity of an operator has already been spoken about. So I believe so. Therefore, the first term, apart from the expectation value of del A del T, I would say second term, which is I h cross integral h star psi h psi whole star a psi from hermiticity could be written as psi star h a psi and minus psi star ah psi. So at the end, we are getting IH cross integral psi star HA minus AH psi dx. So HA minus AH is nothing but the commutator of Hamiltonian H with operator A. So ultimately we are getting the time derivative of expectation value of operator A is full time derivative is partial time derivative of A plus I upon H cross expectation value of commutator of Hamiltonian and operator A itself. So in particular, if our operators do not explicitly depend on time, and mind you, in Schrodinger representation, state vectors, they do depend on time, but operators are independent of time. So in this case, one may write Please go to third slide. Please go to third slide. In this case, one may write del A del T equals 0, and which will give me my equation of motion of expectation value of operator A uh, uh, as IH cross D expectation value of A dt is equal expectation value of the commutator of A and H. And if this is the relation with expectation value for operator itself also, we shall have the same relation IH cross time derivative of operator equal full derivative equal the commutator of A and H. So what do we see that I had, and of course, our students, I believe, already know that every observable year is does correspond to an operator, say A. So if operator is commuting, is a commutator of the operator with Hamiltonian is 0, suppose, then we are finding the full time derivative of operator equals 0, which means operator or the very observable concern is conserved. So for conservation, for observable concern remaining conserved for any length of time, our condition is that the corresponding operator should commute with the Hamiltonian of the system. I believe this result is clear to everybody. Is it clear? Hello?
Yes, sir, it is clear.
Okay, it is clear. Now I would like to go to the next slide, that is what? Fourth slide. Okay. Here I have stated that COs meaning commuting operators. Commuting operators have shared eigenfunctions. Commute meaning operators which commute, they would have simultaneous eigenstate. You can also say so. How we have shown it? Proof is like, suppose we have an operator A and psi is its eigenfunction. And of course, I repeatedly have told yesterday, today also I need to tell, I have to emphasize that first comes eigenvalue, then comes eigenfunction. So I should have stated this way, that let there be an operator A with eigenvalue, let's say small a, and corresponding eigenfunction is psi, then we have our usual eigenvalue, eigenvector relation, A psi equal, operator A psi equal small a eigenvalue psi. Now to this, I operate the operator B on both these sides. Of course, the eigenvalue small a is a number, got nothing to do with any operation. Therefore, A can come ahead in the right hand side, and you have B, operator B acting on psi on the right hand side. On the left hand side, however, you have first A, operator A is acting on psi, followed by operator B acting on A psi. Now, whether because I have assumed A and B commute. So whether I write operators in the sequence BA or AB, they are one and the same. So in the next step, I write in the left hand side A, operator B, psi equal eigenvalue A times B psi. So what does one see? That if psi is an eigenstate corresponding to eigenvalue A of operator capital A, then B psi is B psi, B operator B psi is also eigenfunction of A with the same eigenvalue as psi. Why? Because I have A, B psi I put within bracket equal A times B psi. So equation therefore tells me that if thus B psi is is also an eigenfunction of A with the same eigenvalue as psi. Now, if that is that, then B psi will differ from psi only by a multiplicative factor. So let that multiplicative factor be small b. So you have B psi equals small b psi, and psi thus is also an eigenfunction of the operator B. So commuting operators have simultaneous eigenstates, which means what? They can be measured together. They are compatible variables. Since they are compatible, there is no uncertainty relation between such variables. Position and momentum, they do not commute. X, commutator of position X, and momentum P is IH cross, fundamental commutation relation. Since they don't commute, they are incompatible variable, and they have amongst them the uncertainty relation. That means they do not share their simultaneous measurement with any degree of any precision is not possible. If you measure one with accuracy, other one will become very inaccurate. With this, we go to the
Sir,
seventh.
there is a question from Akshita. You want to
Yeah.
take questions in between or you want to take it at the end?
No, in between will do.
Okay, sir, this is the question. Why does B psi have to be a scalar multiple of psi? It could have been a different state, meaning a degenerate state of A. Sir, question is posted in the chat box.
Yeah. Question is, why does B psi have to be, can you repeat? Why B psi will
Why
have
B
to,
psi have to be a scalar multiple of psi? It could have been a different state, meaning A has degenerate states, question mark.
well, I have not anywhere said B psi is same as psi. I only have said our equation tells me, look at the equation here. in the fourth slide, A, B psi, A operator acting on B psi equals eigenvalue A, B psi. If I interpret this, I simply find I assumed psi was eigenstate of operator A with eigenvalue small a. I am simply finding that if that is so, psi an eigenfunction of A with eigenvalue small a, then B psi, operator B acting on psi, that will be a state only. Why it should be a state? Operator always, operator suppose B is a 3 cross 3 matrix and psi is a 3 cross 1 matrix. So upon multiplication, that is a column vector. Usually the states are given by column vector. I am more, I can visualize things more with matrices, and I believe students also can visualize things more clearly with matrices. Operator, suppose our operator B is any 3 cross 3 matrix and our psi is a column vector, states are always column vector, say 3 cross 1 matrix. Multiply, you get yet another 3 cross 1 matrix, which is what? Yet another state, yet another state. It is not psi. Psi originally was a state like, suppose, a column vector like 1, 3, 2. Now to this, if I multiply a matrix 3 cross 3 matrix, say 2, 3, 1, 1, 5, 0, 2, 4, 3, and to this I multiply 1, 3, 2, I would get yet another matrix. So what I am saying simply is that B psi which I get will also be an eigenfunction, as our equation says, will also be an eigenfunction of A with same eigenvalue, eigenfunction of operator A with same eigenvalue small a, which was the eigenvalue of state psi. So we have a situation here, we have same eigenvalue A, right? That is corresponding to two different states. First state is psi, another state is B psi. Is that clear? Is that clear? Whoever is asking, is that clear?
Yes, sir, it is clear.
Okay. Now, B psi, B is an operator basically. If it acts on psi, our problem formulation or definition of eigenvalue, eigenvector problem, the way we formulate, B acting on psi will give me some eigenvalue small b psi, small b psi, correct? So what is the net result? Psi also is an eigenfunction of B with another eigenvalue, small b. We have psi um, is the commonality between the two operators which are commuting. Not clear yet. Hello?
Yes, sir. So that means B psi and psi are degenerate states of A.
B psi and psi, yeah, they correspond to the same eigenvalue. Obviously, what is their eigenvalue? A.
Okay, sir.
Obviously, eigenvalue A. If psi has eigenvalue, psi corresponds to eigenvalue A, and from our equation we finding B psi also corresponds to eigenvalue A. Correct?
Yes, sir.
Okay. So now we go to the seventh slide, which is talking about where I'm talking about momentum operator. So we have function fx, let us say. Some operator A acting will give me an eigenvalue and the function itself. So I take simplest function, say plane wave solution, plane wave propagating in x direction. I apply momentum operator to this. Momentum operator is h cross upon I ddx, yeah, minus I h cross ddx, which when acts on the function plane wave, that is, will give me h cross k fx. So what does one find? One finds corroboration of de Broglie hypothesis that momentum operator, when acting on a single particle, because plane wave is eigenstate of single particle, acting on a single particle state will give me the momentum eigenvalue h cross k, which is of course is how much? Small h by mb times the function itself. So de Broglie hypothesis gets corroborated, and we find that momentum operator has eigenvalue h cross k, where h cross is reduced Planck's constant, k is wave vector amplitude, 2 pi upon lambda, or h cross being h upon 2 pi and k being 2 pi upon lambda. I can also write this as what? H upon lambda, and that being equated with mb is giving me lambda equal h upon mb, our de Broglie hypothesis. Anyway, that is a separate thing. What is one finding? That momentum operator has eigenvalue h cross k for a single particle state, free particle state. If I take a very complicated system and its eigenstate, momentum operator may not be yielding the eigenvalue h cross k. Only, at least in this simple case, it is yielding that. Then we go to next slide, which is sixth. The energy, sixth slide, energy operator.
Yes, sir.
Yes,
Yes.
sir.
Sixth, energy operator. Well, energy operator, momentum operator, I have seen h cross upon I nabla in 3 dimension, of course, or minus I h cross nabla operator. And position is operator only in momentum representation. In position representation, position remains C number. So anyway, these are fundamental operators. And Hamiltonian operator, which is energy, will be momentum operator square upon 2n plus potential. Potential operator is basically potential we shall assume to be independent of time, independent of velocity and all that stuff. So we have simple potential, which would be again a C number. And well, after that, there is, I don't think I need to explain any further on this because it is already known. So we go to the next slide. We go to the where we have next slide, that is seventh slide, Hermitian conjugate of an operator. This is important. You see, suppose we have an operator and we denote its Hermitian conjugate by a dagger. Operator in matrix representation, as I said, is say in Gaussian matrix. A dagger is what? Transposition followed by complex conjugation at the matrix level. So Hermitian, taking Hermitian conjugate is also called adjoint of an operator. But at the differential level or wave function level, take the right hand side, which is expectation value of operator A. Why? Because operator A in the right hand side is sandwiched between psi star and psi, and it is integrated over entire space. And on the left hand side, we have conjugate of Hermitian conjugate of operator A denoted by a dagger. A dagger, if the expectation value of operator A is a dagger psi star psi dx integrated over all space, then a dagger will be called the Hermitian conjugate of operator A. Is the definition clear? Is the definition clear?
Yes, sir.
Okay. Now, the Hermitian operator has special relevance in quantum mechanics because why it will immediately be clear. It will be shortly clear. Now, an operator A will be called Hermitian if the expectation value of the operator is a psi star, a psi whole star psi dx. That is the definition. So with this definition, if any operator obeys this definition, it is called Hermitian. I have taken the most simple example of position operator. I started with left hand side position operator into psi, whole of it with star psi dx. Now position operator in our position representation is merely a C number. So in the next step, I have removed the hat from X, one can see. So you have only a number which is position X, psi, whole of it star psi dx. And X psi star, whole of it star is psi star X star. A B star, AB whole star is B star into A star. This is, I think, a well-known result. So with the help of this well-known result, I write XI whole star as psi star X star, but X is a number, real number position. Position cannot be complex. So we have X star equal X, which is nothing but your expectation value of position operator. Therefore, from the definition, it is clear that position operator is Hermitian. Next, I have taken momentum operator, which is minus IH cross ddx. I wish to show this is Hermitian. So we started with left-hand side where we have operator P psi acting on psi, whole of it star psi dx equal, write down what operator P corresponds to, minus IH cross del psi del x, whole of it star psi dx. And taking complex conjugate of minus I will give me plus I. So we have plus I H cross d psi dx star psi dx. Now d psi d integral d psi dx star psi dx to be integrated by parts. And integration by parts, I am sure, is known to everybody. So, and we now also recognize the fact that wave function at infinite distance, say at the edge of the universe, would be zero. Particle cannot go up to the edge of the universe. So we have thus, in the after partial difference or integration by parts, we have minus IH cross psi star d psi dx dx, and I minus IH cross d psi dx is nothing but momentum operator. So ultimately we are getting expectation value of momentum operator. Thus we have been able to prove that even momentum operator is Hermitian. Next is our eighth slide. No. Uh, Next slide, please. It would be eighth, isn't it?
Yes, sir.
It would be eighth. Okay. Okay. So I have written down here once again that, all right, momentum is Hermitian operator. Now, Hermitian operators have two important properties, and they form the basis of quantum mechanics. Eigenvalue of Hermitian operators have to be real. Why so? Reason is observables are like position, momentum, angular momentum, energy, etc. They are real numbers. Their measurement will yield real numbers. So operators corresponding to uh, uh, energy, momentum, linear momentum, angular momentum, etc., they should or be Hermitian operator. So you see the connection now that eigenvalue of Hermitian operators have to be real. Your observables are represented, everyday observables in physics, represented by Hermitian operator. Their measurement would, their eigenvalue should be real. Reason is everyday observables are not complex. None of them. Position is not complex. Momentum is not complex. Energy is not complex. So I believe my explanation of why eigenvalue of Hermitian operators have to be real is clear. Secondly, eigenfunction of Hermitian operators are orthogonal to each other always. Or if they are not, Suppose they can be made orthogonal by taking linear combination of them. Orthogonal operators, sorry, eigenfunctions of Hermitian operators are orthogonal to each other. Why that should be so would be made clear later. But first part, of course, is that the eigenvalue of Hermitian operators have to be real. I'm going to prove it just now. I believe physical reasoning is clear to everybody. Observables are to be represented by Hermitian operator. They are never by, they always satisfy Hermiticity condition. And since these observables give me yield a number after measurement, so their eigenvalue will have to be a real number, not a complex one. And an operator can have operator will have eigenfunctions. Hermitian operators will have definitely their eigenfunctions belonging to different eigenvalues, and why they should be orthogonal to each other, that we shall come to later. We go to the next slide, where that is ninth slide, where we show that kinetic energy is Hermitian. So once again, we started with kinetic energy psi star psi dx and half 1 by 2m p square psi star psi dx. And then we wrote it as, because p square could be splitted, momentum operator square could be splitted into two parts, P and P psi. So we have P psi star P psi dx, which of course once again taken conjugation psi star P square psi dx and P square upon 2m giving me kinetic energy back. So we have expectation value of kinetic energy. Thus, kinetic energy also is Hermitian operator. It ought to be. Now, in the very next slide, that is...
Sir, there is one question. Student is asking why psi star is always written before psi.
why psi star is written before psi?
Yeah.
Well, uh, uh, there is a reason. There is a reason. Actually, if one follows Dirac bracket notation, psi will be something like a conical bracket with pointed end pointing towards right. Getting me? Psi will be a pointed end pointing towards right. On the other hand, I'm talking about Dirac bracket notation if students are following that. On the other hand, psi star corresponds to the same bracket with Dirac bracket with pointed end pointing towards left. Now, if I have to find expectation value of an operator in Dirac notation, I sandwich the operator between two Dirac brackets, one having pointed, the first one having pointed in towards left, second one having pointed in towards right. This is a matter of convention. So with that convention, we are writing, I think probably, on the other hand, if I invert the sequence, that is left, that is beginning with a bracket which has pointed in towards left and ending with another bracket which has pointed in towards right, beginning with a bracket which has pointed in towards right and ending with bracket which has pointed in towards left, I will not get the expectation value. What I will get is an operator. Why operator? The reason is it is a case of, if you see, I visualize things better with matrices. So suppose I have a column vector, uh, uh, say any column vector 1, 2, 3, and this is a 3 cross 1 matrix. If I multiply to its right a row vector which is 1 cross 3 matrix, what matrix shall I get? A 3 cross 3 matrix which will become an operator. Column vector always state, operator always n cross n square matrix. So these are conventions. This is why in writing uh, uh, your expectation value, psi star I put towards left, so that there is a kind of harmony with Dirac notation. I think that is the reason. Of course, this lecture will be followed by Professor Dasgupta's lecture. So if student asks him, probably he can shed better light on this aspect. I think this is what I can say with regard to this question at the moment. Can I proceed?
Okay, sir. Yeah.
I go to proving that which I have been repeatedly saying, like parrot, Hermitian operator should have real eigenvalues. Physics demands that. How? So I take a Hermitian operator. In the next slide, that is what I do. Eigenfunction of the operator is psi, corresponding to eigenvalue small a. And I take integral of a psi star psi dx. A psi, operator A psi will be from above small a psi star whole star psi dx, and A psi whole star will be A star psi star A star psi star psi dx. Now A star is a number gone outside the integration. I have psi star psi. Now with this we go to the next slide, please. Now we do the same and look at it through hermiticity of A. After all, our A is Hermitian operator. So integral of A psi star psi dx by hermiticity would be psi star A psi dx. But A psi is nothing but small a psi which has gone outside. So once again you are getting A times in total integral psi star psi dx. So you have two equations. In one equation, your left hand side is giving me A star integral of psi star psi. In the second equation here in this slide, the left hand side is giving me A integral of psi star psi. So A star minus A should be equal integral of psi star psi dx, that is 0. But integral of psi star psi dx cannot be 0. This is total probability. So you have A star equal A. Well, that means complex A, assumingly here is a complex number. So if a complex number and its complex conjugate are equal, then the number is real. So eigenvalues therefore will be real, and this proves the result. I think the proof is clear to everybody.
Yes, sir, it is clear.
Okay. Next, we go to some discussion regarding this. You see, I have eigenvalue of Hermitian operator real. A real eigenvalue means physical quantity for which operator stands for can be measured experimentally. Measurement will give me a real number. Eigenvalue of two commuting operators can be computed using common set of eigenfunctions. As students may see, say we have in our Delhi University syllabus hydrogen atom, one electron system in Coulomb's potential. So one would be able to show that the Hamiltonian of this system and square of the angular momentum they compute. That means square of the angular momentum and the H operator of one electron system, they have simultaneous eigenstate. Similarly, one can show that hydrogen atom Hamiltonian and Z component of the angular momentum would commute. So they have therefore shared simultaneous eigenstates. And lastly, I have written if two operators commute, they have simultaneous eigenstate. So their measurement could be possible simultaneously with utmost precision. And for such compatible variables, the uncertainty relation is not valid. Uncertainty relation is valid only with incompatible variables. Now I have given to Madam two more uh, slides, little back ones. Have they been forwarded to
Yes,
you by
yes, sir.
Madam?
Yes, sir. They have been forwarded. Before
Yeah,
that, there is one question.
yeah,
Uh,
yes, yes. What is it?
uh, Madhu Pandey says, how can we write p square equal to p dot p?
P, P square, P is operator or uh, uh, number?
I suppose p is operator.
Operator, I never write dot. The operator ke liye to dot has no meaning. Operator is something like ddx, ddx, d2x, dx square. But dot ka kya mean? Dot always is used for three-dimensional Euclidean vectors. And in the quantum mechanics case, three-dimensional Euclidean vector ka jo dot product hai, that is generalized to an inner product of a state vector, let us say mu, with pointed end towards right, and a state vector lambda with pointed end towards left will be equal eigenvalues lambda star mu. This is and of course it will sum over I, because lambda I is suppose an eigenvalue, mu I also is an eigenvalue, and an eigenvalue, and I could be several, I can have several values. So lambda star, lambda I star mu I sum over all I. This is inner product generalization of what you call generalization of dot product in the case of three-dimensional Euclidean vector. This inner product always is taken between state vectors which belong to our what you call Hilbert space. So Hilbert space basically is a vector space of a complex vector space where inner product is defined. So I have never written operator P dot P that has no meaning. Where have I written? Can student show? Hello?
There is one more question. Akshita is asking, what does simultaneity mean in this context?
Simultaneity simply means आप जैसे let us say position, momentum and kinetic energy of a single particle, right? Their commutator is zero. Their commutator, I think student understands, is zero. And since their commutator is zero, they have what? Simultaneous eigenstate. इसका ये मतलब है कि momentum and kinetic energy both could be measured simultaneously with an arbitrary degree of precision. ऐसा नहीं होगा मोमेंटम पोजीशन के केस पे जैसा होता है कि momentum I have measured very accurately and position has gone haywire. ऐसा नहीं होगा. Is the answer clear?
Yes, sir. One question is, the commutator has no time dependence. Then why do we conclude commutation as simultaneity?
Simultaneity मतलब अब थोड़ा सा misleading usage है. I think I just now have explained. By that I mean here is the measurement of both could be made with with any degree of, with arbitrary degree of precision. ऐसा नहीं है कि एक को मेजर करने से the measurement of the other will go haywire. Is that clear?
Yes, sir.
Of
It is
course,
clear.
student is right in pointing out that we are using Schrodinger representation, although I have not stated that very, where state vector is time dependent and operators are time independent. तो फिर time independent है तो simultaneity की बात कैसे आई? Very good question, very well framed, but simultaneity. Okay, let us jettison the word simultaneity. Let us say they have same eigenstate, shared eigenstate, and that means both could be measured with an arbitrary degree of precision together. The measurement of one will not affect in adverse way the measurement of the other. Is that explanation all right?
Yes, sir. It's all right.
Okay. So I have given, because time and again I have been saying that matrix representation is a better way to understand. So I have solved here two problems. Please show those two separate slides. Hello?
Yes, sir. I'm downloading that presentation.
Right. There are two black slides, blackish. Yeah, yeah. Can you focus? Can you zoom on it? Yeah. Okay. Okay. I'm sorry if right at the outset I would say that I have not been able to put a matrix Wala notation like the big bracket. So we have an operator R. Suppose it is given by a 2 cross 2 matrix. I've taken a fictitious problem. 6 minus 2 on one row, minus 2, 9 on the second row. So very easy to understand that I have this matrix is, as I said, the square matrices correspond to operator. Well, I have not shown, but probably it's been shown already. So this is our operator. Now, square of R will be matrix square, which is 40 minus 30 minus 30, 85. My task is to find expectation value, because I've been talking about finding expectation value. I began with that. Expectation value of the operator R square is to be obtained out here using an arbitrary state vector. What is that arbitrary state vector? Psi. Psi is a column vector with elements A and B, and psi dagger is a row vector transpose of it followed by complex conjugation. Therefore, the transpose of it, so row vector followed by complex conjugation, that is A star, B star. And suppose A, B obey a condition. A condition is absolute value of square of the absolute value of A plus square of the absolute value of B is equal 1. With all these paraphernalia, I am to find expectation value of operator R square. So, as I said, matrix representation and our Schrodinger representation in terms of differential and integral, that has to be brought at par, and there should be a complete harmony. So the harmony demands that expectation value of R square should be psi dagger R square psi. Now psi dagger is the matrix A star B star row vector. R square is the square matrix 40 minus 30 minus 30, 85, and psi is AB, the column vector. Multiplication of matrix multiplication is too fundamental, too easy. I therefore have not shown the detail, but I have written down the final result, which is 40 multiplied by square of the absolute value of A, 85 multiplied by square of the absolute value of B, minus 60 multiplied by A and B, they could be complex. So 60 multiplied by real value of A star B. So this is what I get as my expectation value. So our students have seen one way of finding expectation value of operator, which I showed through Schrodinger approach, and through this matrix approach of Hassenberg, Pauli, etc. The expectation value determination is simply boiling down to a matrix multiplication. Of course, one has to remember here, I again repeat, state vectors they belong to a complex vector space where the inner product is defined, which is called Hilbert space, and they are represented by state vectors represented by column vector or row vector, and operators acting on state. Operators will have to be represented by the row, by square matrix, like any n cross n matrix. In fact, if you remember this particular stuff, everything becomes calculation of expectation value, etc. through matrix becomes rather easy, not difficult. I have next slide, please. I have in the next slide, suppose there is an operator K. It is acting on state 1. State 1 could be our usual 1, 0, 0. The three basis vectors in three-dimensional Euclidean space are I, J, and K, and their matrix representation would be 1, 0, 0 column vector, 0, 1, 0 column vector, and 0, 0, 1. So state 1 is the one of the basis vectors. So K operator acting on 1 is, suppose operator is such that it is giving me eigenvalue 2 and the state back. Similarly, K operator acting on 2 is giving me eigenvalue 3 and state 2 back. K operator acting on say state 3 will give me suppose eigenvalue -6 and state 3 back. ये मेरा सपोजिशन है, ये मैंने मान लिया कि K operator it is an operator. It acts on state 1 gives me eigenvalue 2, acting on state 2 gives me eigenvalue 3, acting on state 3 gives me eigenvalue 6. लेकिन इससे तो operator नहीं बन पाया. To make an operator, I have to construct K operator. 2 multiplied by state 1 has to be multiplied by 1 star, which means state 1 if has conical bracket pointed towards right, 1 star will have conical bracket pointed towards left. Similarly, 3, 2, 2 star conical bracket pointed towards left, -6, 3, 3 star conical bracket pointed towards left. And as I told you, 1 is 1, 0, 0, 2 is 0, 1, 0, 3 is 0, 0, 1. So this matrix K operator finally will correspond to a diagonal matrix where diagonal element will be 2, 3, -6 and off diagonal elements will be 0. ये जो K operator 2, 1, 1 star है, 3, 2, 2 star है, -6, 3, 3 star है, इनको matrix form पे ला करके when you multiply, you would finally get a 3 cross 3 diagonal matrix with diagonal elements 2, 3, -6 and off diagonal elements 0. I have written it in a short notation, which of course is not followed in textbook, because in textbook there is nothing like state 1 within bracket. It is actually Dirac bracket that is used, but typing Dirac bracket in a slide is slightly difficult proposition for me. So therefore, I have resorted to my own notation. And suppose I have a state theta, and this state theta I have denoted by -3 state vector 1. You see, state vector, like your three-dimensional Euclidean space पे अगर किसी vector को if you wish to write, then vector A will be written as A1i, A2j, A3k, where I, J, K are the unit vectors. They are linearly independent. They are orthogonal to each other. In fact, orthonormal. And vector is written as component multiplied by these linearly independent which are called bases. Component basis ka sum. So you have state vector theta as some component -3 uh, and vector 1, which is 1 0 0 5 2 7 3, and it is orthonormalized, so you have divided by square root of 83. So now I am asking you to find expectation value of K operator with the state theta. So once again, it is only a expectation value finding is only matrix multiplication, nothing else. You can see that on the left hand side, I have written, uh, uh, say, the state in matrix form, actually a row vector, 1 by square root of 83, -357. And then I have written the operator, which in short notation I have, which is actually a 3 cross 3 diagonal matrix. I have simply written diagonal 2, 3, -6. And then I have multiplied it with our theta, which is 1 by square root of 83, column vector 3 -357. And this matrix multiplication, if you perform, you will get the answer -201 upon 83. So expectation value of an operator in a given state, arbitrary state, a given, could even be negative. That's what I wanted to drive home. Don't ever think that expectation value has to be something like positive, right? It could even be negative. And don't ever think that the expectation value is same as the most probable value. Most probable value is a different story altogether. So I believe with all this, people have understood the basics. These I have deliberately uh, inserted wherever I found uh, tempting the matrix notation. Although to begin with, quantum mechanics in our at UG level is not taught with matrix notation. So, but you see, with matrix notation, things are simpler to handle. At least I find it very easy to handle. That's all I have to speak. I take. Thank you very much for patiently hearing me out.
Thank you so much, sir. And it was a really nice talk. I'm sure students must have learned a lot from it.
Thank you, man. Thanks for nice words. Any query from student side? Hello. Hello. Any query from student?
Sir, no questions are there right now in the chat box.
Okay.
So thanks a lot, and um, we welcome our next speaker, Professor Patrick Das Gupta. He's
Hello,
here.
everybody. Are you able to hear me?
Yes, sir. We can hear you. We can hear you.
Yeah. So my desktop internet is giving trouble. So I am logged in from my mobile phone, which is called Baba's iPhone.
Okay.
And you have received
Yeah,
the
yeah, yeah.
PDF
We
file,
have
right?
received the PDF
Right,
file.
right,
So,
right. So what you can do is you can screen share that PDF file, all right,
sure,
which is
sir.
called
Sure.
quantumlectures.pdf.
Sure, sir. Sure.
Great. So is this
Is
visible to
this?
everyone?
Is it visible? Dr. Mansi, can you share the intro slide of sir first?
Yeah, sure,
Uh,
sure.
first.